Okay, welcome back to classes. I know a lot of you are a little nervous about exam 2 coming up. And so let's talk a little bit about exam 2. And I'll finish lecture today with some specifics on exam 2. We're going to stick to the schedule that's in the syllabus. And so in other words, it'll be Thursday in lecture, 50 points. And it will cover everything from lecture 9 up to today, lecture 15. So everything that we get to in chapter 6, we won't get to all of chapter 6 today, but we'll get to a good portion of it. So basically that means chapter 4, energy and momentum, chapter 5, angular momentum. The extra lecturing I did on universal gravitation. Last Tuesday, special lecture on hurricanes and atmospheric pressure. And the atmospheric pressure and pressure concepts in general are actually in chapter 6, although I didn't write about them in chapter 6 in the context of hurricanes, but you can definitely read about pressure in chapter 6. And then item 5 on this little mini outline is basically everything that we cover in chapter 6. Some of the brain burners of chapter 6 will leave for next Tuesday. We'll kind of get some of the basics down today, and I'll quiz you on those. By the way, you will have some homework tonight. They'll both be kind of, I'm going to give you a tiny homework concerning today's lecture, and another a little bit bigger assignment, but it's going to be a little review assignment, kind of like I did last midterm, 4 weeks ago. Okay, SI session review. SI review session, that's today at 3 o'clock, classroom building 1, 3 o'clock to 4:30. Be there if you can. And as always, I encourage you to go, even if you can only make the last 20 minutes, or you can make it at 3, but then you have to leave at 4:15 or 3:45 or something. Just go. Go as long, and Maria, she doesn't mind if you can only go for a short amount of time. Because every minute that you can spend in there with the SI review is going to help you. Also, there's going to be regular SI review tomorrow, and you have a Tuesday session. So the Tuesday session today is the review session. And then there's 2 more tomorrow, 1 at 11, the regular schedule, and then the online session. Speaking of the online session, we now have recordings of all the online SI sessions back to August 28th, I believe. Maria recorded them, and you can review them. In other words, you can listen to the audio of Maria and everybody else talking. You can see their text, because some people don't have a microphone, so they can't text, but they can't speak into the session and be recorded like Maria. But they can, of course, text. You can see all that. You can see all Maria's diagrams and stuff. I use the same software. It works really nicely. And on the SI schedule page, there's a list of links to those separate recordings. So the SI page, here's what it looks like when you click onto it from the home page, the SI schedule page. There's a picture of Maria down there. And then if you focus in, there's now a link here that says click for recordings. So if you click that link, it'll take you down to the bottom of the page. And there it is, down there towards the bottom. There's 5 of them. So August 31st, all the way up to September 28th. So that's pretty good. And then she'll have another session tomorrow night, Wednesday, 4:40 p.m. Okay, questions about that? Okay, let's keep talking about heat energy. And this is a photo from Florida supercell. Boy, if I saw that coming, boy, I'd be kind of nervous. Matter of fact, one time I was driving back from Fort Lauderdale, and I did see, we came up through the Everglades, Lake Okeechobee, and up through that way. You see forever. And there were thunderstorms to the left of us, to the right of us, and we were kind of trying to thread the needle there, and then we got stuck, and they could be pretty ferocious. Those systems are convection systems involving water vapor, and water liquid, and we're going to be talking about that today. Here's a diagram from page 93 that is kind of a theoretical picture of the three states of matter: gas, liquid, solid, and the phase transitions: sublimation, vaporization, and fusion. And we're going to be talking about this picture today quite a bit. And if you think about it, we have been talking about Hurricane Matthew. Boy, have I got a headache. I'm sorry, students. I get migraine headaches sometimes. I can feel one starting. Oh. All right. Yeah, Hurricane Matthew. Hurricane Matthew, dramatic weather, catastrophic. Raise your hand if you live over in Brevard, Volusia, or oh gosh, or Flagler. Oh man. Okay. Is there? You guys that raised your hands, did your house get blazed up badly? I had a student last hour that came in and said, Dr. B, I lost everything. She lives over on Merritt Island over by the Space Center. If you are experiencing, if you lost well, you can't lose your textbook, it's an ebook, but if you lost your notes or something, you need any kind of assistance, we'll try to, just talk to me after class, we'll try to help you out. We got the other student that lost everything. She just got totally flooded out. So all of her stuff is out at sea. She doesn't know what to do. We're helping her out. We're getting her squared away. And we'll get you squared away if that applies to you as well. Anyways, Hurricane Matthew, gigantic system, and basically the dynamics are liquid to gas, gas to liquid, based on the exchange of heat between the surface of the ocean and the water vapor in the atmosphere. So here's another area where we want to know all and use as much of the information that we have about the phase transitions, specifically for water and CO2. That is the topic of moon bases and establishing a base on Mars and a base on the moon. Here's a picture of a NASA test vehicle. Notice anything about this picture, this photo? It's a Mars vehicle. What do you notice?
There's a person inside.
Well, yeah, I guess there is a person in there. I didn't notice that. Anything else? I mean, it's a vehicle, right? Okay, it's not a robot, it's a person, but I mean, it better have either a person or a robot. What do you see? Yeah. Huge hatch, yeah. Anything else? What do you see, Nick?
The mechanism that's attached to the tires looks like it has some pressure involved with it.
Yeah, pressurized shocks here. Notice anything curious? There's no clouds. Yeah, there's no clouds. Is this Mars or Earth? It's Earth. It can't be Mars. Look at that blue sky. Look at these plants. So it's actually a big lava flow down in Arizona, down by Flagstaff that they use. You should be taking notes now. Here's a picture of these guys trying out suits and other vehicles. And, you know, the thing about Mars, it's extremely arid. And they use these lava flows to test vehicles, you know, the rovers that they have and spacesuits like this. Where I used to live in Montana, there's this place called the Pryor Mountains. And if you go to the Pryor Mountains and you go out there far away from the roads and stuff, you know, like we used to go there and look for fossils. It's a pretty cool place to find fossils. But you go out there in the Pryor Mountains and you would think you're on Mars. It's just, everything is red, rock, arid, dry as a bone. It's amazing. Here's another picture of these guys, you know, on that cool looking vehicle. And it's not just trying out stuff in Flagstaff. I mean, the whole thing about exploring Mars, the whole thing about exploring the moon is we want to eventually colonize. That's our dream. And right now it's still a dream. It's not factual. We actually have established temporary bases on the moon when the Apollo astronauts were up there. But then they were vacated after, you know, a day or so, a few hours. But we want to have permanent bases up there on the moon and on Mars for various reasons, colonize them and so forth. And so what we wanted most, the thing that they most want to find and locate, measure the amount of water. Water. Water on Mars, yeah, there's a ton of it. Water on the moon? Yeah, we think that there's some water on the moon. The water on the moon, they've had various spacecraft orbiting the moon looking. And what they do is they try to look directly into the craters on the North Pole and the South Pole of the moon. And in the deeper craters, they've found water ice. And they've actually sent a couple rocket boosters to impact and crash land in some of those craters and see if the debris, you know, the smithereens that go blazing up into the atmosphere or up into the sky of the moon, see if they contain water. You know, they send in the rocket booster and it explodes on the surface and all the smithereens, they look to see if there's water there. And they found it. They're pretty sure that in these deep craters, there's still ice. And the reason that it exists up there is in those craters, if an asteroid impacts that's carrying a load of water, the moon is going to gravitationally acquire some of that water. And if it falls into a crater that's outside the sunlight, that doesn't get any sunlight, so that's the north and the south poles of the moon, it'll stay. It'll just stay frozen. And that's what they think that they've got. And they've found water on the moon. We've got spacecraft like this one, the Mars Reconnaissance Orbiter, orbiting Mars. And this is a picture of it kind of floating. Actually, this is an artist's conception image of the Mars Reconnaissance Orbiter orbiting over the polar ice cap. Now, here's a side comment for you about Mars. The polar ice cap on Mars is mostly CO2 ice, okay? Mostly carbon dioxide. There's water ice, and we find water ice other places on Mars, but the polar ice caps are mostly CO2 ice. It's kind of cool. This Mars Reconnaissance Orbiter, you can make a note of it. It's got radar. It's got infrared. It's got visible light. It's got, I believe it's got ultraviolet cameras. And they're just trying to observe as much as they can because they know that if they see certain spectra like we did, you know, hydrogen and helium and neon, they're looking for the spectrum of water. which is has a lot of spectral lines in infrared, actually. Now, I mentioned radar. They have what we call a ground penetrating radar. And the ground penetrating radar on this spacecraft is similar to the ones that the U.S. put in space back in the 60s. Back in the 1960s, they wanted to be able to look down and see what the Russians were doing during the Cold War. So they developed a radar that could, a ground penetrating radar, and they could see all the Russian missile silos. And they knew exactly how many there were and where they were and all that. So the Russians couldn't trick anybody. And of course, the Russians were able to develop the same tool, and it makes things safer because nobody can make a mistake. Everybody knows what's happening. And but they first unveiled their technology in the pages of National Geographic magazine. They have this orbiter up in space, and every fraction of an orbit, it's going over the Soviet Union. But most of the time, it's floating over the ocean. It's just mapping the ocean. But a lot of times, it's moving over other continents. And so what they did was they made a study, a radar study, of buried canals and waterways in the Nile Delta. And the Nile Delta of Egypt, a lot of those things that were built back in the days of the pharaohs and stuff, they're all covered over with sand. But you could see them with this ground penetrating radar. So they made this cool article. I should look it up one of these days. An article in National Geographic, The Wonders of Egypt, the wonders of the Nile Delta, uncovered mysteries of the Nile Delta. And what they were really doing is saying to the Russians, yeah, we see all this underground stuff in the Nile, clear as a bell. And so we see everything you got, clear as a bell, in those missile silos and every underground installation that they had. So now we have it up there on Mars, and they're looking for water, and they found buku water, tons of water. And apparently, the water ice in Mars is below the surface, so it's like a lot of ice covered with dirt, which is like the tundra up in, like Alaska, the land of the midnight sun, permafrost. Ice is permanently frozen until you build a fire or something, I guess. It can melt stuff. So they sometimes see stuff melting on the surface of Mars. Here's an image that they put together. This is actually probably about 1,000 images that they put together of a place called the Hale Crater, or near the Hale Crater. And those dark streaks to the left, the lower left of this image, are the signs of flowing water, flowing liquid water, made recently. Maybe not yesterday, but not 2 years ago. That's new stuff. And question. This stuff, let me get my cursor. This stuff right in here, from the middle left down to the middle bottom. Okay, these streaks. Now, this is a false color image, so that's not like snow. It's not like you're out in the northern Rockies or something like that. But yeah, this stuff here is supposedly the signs of water and flowing water and recent. So it's not like a million-year-old flow of water. It's like, recent months and days ago. So they can't keep an eye on everything on the planet of Mars. They don't have enough satellites for that. But this one they did find. It's kind of cool. It even looks like a mountain range on Earth with glaciers and stuff. Okay, so this is where the Hale Crater is. It's down the southern hemisphere. This thing here, this kind of crease here across the surface of Mars, back 100-something years ago, when they first observed this, they thought, whoa. They didn't have this beautiful, precise image, but they saw lines, and the lines changed colors during the year, and they thought, whoa, those are canals. Because it does look pretty straight. And so they thought, whoa, those are canals. There's Martians, and they have canals, and the leaves bloom, or the leaves grow leaves according to the season. The leaves fall. So they thought they were looking at vegetation. But really what it is huge dust storms that obscure that for huge portions of the year. And so if you miss it, you think that the canals are dry. And then if you get it a little bit later, you think, oh, the canals are lush with foliage. But it turns out it's a huge canyon, and it was caused by water, they think. And we're still trying to figure it out. A lot of stuff up there. So this whole idea of phase transitions, solid water to liquid water, that's what we want to know. We even have a spacecraft called Kepler that searches out stars in a portion of the sky near us that have planets, exoplanets they call them, EXOPLANET, exoplanet. They're looking for exoplanets, and they found hundreds. And what they're really looking for is a planet the size of Earth, or about that size, and a certain distance away from their star, and a planet that has signs of water. Because we think if there's water, there might be life there. And if there's life there, then maybe we can communicate. And if we communicate to them, hopefully they won't destroy us, or send robots or something like that. Anyways, we want to know all about the presence of water all over this place. Now here's a picture from page 116. And we're going to tackle the brain burner that is associated with this image on page 116. But we're actually going to talk about this image for certain of the things, phase transitions that we're talking about today. All right. Now, so make a note, page 116, and we're going to come back to this diagram. Now, last time we talked about the e pluribus unum principle in the context of atmospheric pressure. And so for page 98, approximately, there's this diagram there, and this is like an idealized view of a gas molecule impacting the side of a container of gas, one recoil interaction. So an exchange of momentum, delta P to the right, negative delta P to the left. Kind of an idealized view from page 98. And the thing that I want to emphasize to you, the e pluribus unum principle, is we can't see those molecules. We can see some molecules now, but like 10, 15 years ago, no, you couldn't see molecules. We've just developed the ability to see a few simple molecules. It's very tough with electron microscopes. But most of the time, we can't see what the molecules are doing. So the pressure that you feel, or the pressure that exists inside of a container like a balloon, a balloon is a very simple container of high pressure air. You blow into it, it expands, and it's all caused because of these minuscule, submicroscopic, and tremendously abundant recoil interactions. You can't see the gas molecules, and you couldn't even write down the number of molecules in this room. It's a huge number, but they're so tiny. I mean, we need them to live. We need oxygen to live, but we don't actually see any oxygen molecules. But we know they're there because they're exerting pressure, and they have a temperature. Now, I have an IQ test question for you. Concerning gases and interactions, recoil, and so forth. So get your iClicker ready. And Miss Caroline is up here operating the clicker machine. And here's my question for you. A dense gas, highly concentrated. Just close it. All right, there you go. Okay, you can start to vote. Has blank recoil interactions per second as compared to a sparse gas. Very diluted. Can you click the histogram, the bar chart, and that'll just give us a live view. That's good. See how they change there? It's kind of cool. 20 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Click. All right, you guys did pretty good. The answer is more. And for those of you that answered fewer, here's the concept. You might want to add this to your notes. As I've mentioned before, having notes or using the clicker questions for notes, additional notes, is a helpful thing to do. And the basic idea is simply this, that a dense gas means there's more molecules per cubic centimeter, more molecules per cubic light year, more molecules per cubic whatever you want. And therefore, for every square centimeter of surface, there's going to be more collisions. Now, here's an informal, kind of colloquial way to think about the difference between sparse gas and dense gas. A dense gas is like being out in a rainstorm where it's raining cats and dogs. Okay, so you're gonna get soaked to the bone. So if you go from garage H over here up to this building, and if it's really coming down cats and dogs like it was last week, if just 30 feet, 40 feet, you're going to get soaked to the bone. But if it's just kind of drizzling, you can walk across campus and you hardly even feel it, that you're wet. I mean, you will be wet, but not soaked. And so that's the difference between a dilute gas and a concentrated gas. There's just more raindrops per cubic centimeter in a downburst or in a cloudburst. Now, I want to point out one more thing concerning this diagram, and that is, if this wall over here is movable, then you can say that the gas has done some work, some F delta X work, all right? So here's a way to think about it. A container that's got a movable wall, a balloon. You blow into the balloon. You got to really, exhale hard, and the balloon expands. And so the walls are getting force. They're getting some delta X and some, delta Y in another direction, delta Z in the other direction. So you're getting some F delta X type work because of the pressure that you exert. All right? And so you can say that a gas does work. Another way to think about it, and you may have noticed this before. If you let the air out, I think I've noticed this. If you let the air out of a bike tire, it's actually kind of cool. All right? So you can cool something. You can extract energy, or you can add F delta X to a gas, and you can see the effect of it by moving the wall or expanding the balloon or whatever the container is. Here's another example of a container where at least one of the walls can move. That is the piston in an internal combustion engine. The cylinder is filled with a little bit of vaporized gasoline. The spark plug fires off, causes a little tiny explosion, and the gas pressure expands the piston upward, and that drives the drivetrain. And that's how you go from point A to point B in an internal combustion engine. Now, if you have an electric car or something, it's different, but that's just an electric motor. But F delta X work. So this whole idea of energy and work and temperature is associated. And so let's take a look at temperature scales. And we'll just go briefly through the three basic temperature scales that are customarily used. And there's other ones, but the first one is Fahrenheit, 180 degrees of separation between the freezing point of water and the boiling point of water. All right, now everybody knows about that. And that's reflected in this diagram over here on the far right. 212 is the boiling point of water, excuse me. And 32 right here is the freezing point of water, so 180 degrees of separation. Oh, 180 degrees. You think that's a coincidence? No. Celsius, 100 degrees. Celsius is metric, so they went with a power of 10. 100 degrees of separation between the freezing point and the boiling point of water. So that's the middle scale here, this middle kind of thermometer looking thing here. Okay, so up here, the boiling point of agua in the Celsius system is 100 degrees Celsius. And the freezing point is 0 Celsius. All right? And that's why the ratio between Celsius degrees and Fahrenheit degrees is 5/9, 100/180, 5/9, or 9/5 the other way. The third scale, and the one that we are going to use principally in this class, is called the Kelvin scale, and it is defined differently. It is not oriented to the behavior of water specifically. It is already oriented to the theoretical 0 point of all matter where you can no longer extract work. You know that, the balloon expanding, we could get a little bit of work out of that. I mean, we don't think of a balloon as doing work, but a piston engine, yeah, that's a heat engine. That does work, and that's how we get from point A to point B. When you're heading to Publix to buy some pizza, yeah, that's how you get there. All right? So, but theoretically, there's a certain temperature at which you can no longer get any of that kind of F delta X out of the machine. And that's called the absolute 0 point of temperature. And so that's down here. The Kelvin scale is usually denoted with the letter K. And we don't call them Kelvin degrees, we just call them kelvins. And I'm not really sure of why that is, but I'm sure maybe I knew it once and I've forgotten. But we call them, customarily, we call them kelvins. Over here we call them Celsius degrees. But over here we call them kelvins. So this is the point, absolute 0. So we can get down, we can lower the temperature by extracting work. That's how your refrigerator does things. It heats something up and it expels the heat. And the stuff inside cools down. But at this point, we can't get a refrigerator to refrigerate down to absolute 0. Now, we can get really close, down to like 0.000001 kelvins. But to exactly 0 kelvins, theoretically, you can't get there by conventional refrigeration or any other method. But the other thing about it is, here 3b, that you want 100 kelvins of separation between boiling and freezing points of water. So that makes it a metric scale as well. So this is like starting your graph paper at the bottom of the cliff versus the top of the cliff. So the Celsius scale is starting at the top of the cliff, the absolute scales or Kelvin scale starting at the bottom of the cliff. And so the conversion from Celsius to Kelvin is 273. Okay, so whatever Kelvin is, add 273, or excuse me, whatever the Kelvin temperature is, subtract 273, and you'll have the Celsius temperature. And similarly, the other way, whatever the Celsius temperature is, add 273, and you'll have the Kelvin temperature. So it's pretty easy to convert, just add 273 or subtract. And that's the one that we're going to be using. So, and by the way, let me make a note here concerning exam 2. There's not going to be any obnoxious conversion problems between Celsius and Fahrenheit. I have a lot of hatred for problems like that, and so I'm not gonna. If I hate something, I'm not gonna make you guys do it, because there's so much cool stuff to ask you about and think about, and conversion stuff is boring, so we're not going to do it ever. Now, the only thing that you are going to have to remember is going from Celsius to Kelvin, and the reason for that is sometimes, actually, in this textbook, I've written most of the stuff in kelvins, but occasionally you'll see in other textbooks Celsius. So we'll probably, like on the exam, we'll probably have one really cinchy Celsius to Kelvin problem, and then everything else will be all kelvins. So you won't have to worry about it. Yes?
You said when going from Celsius to Kelvin, it's add subtract 273.
Yeah, so to go from Celsius to Kelvin, so for instance, water is 0 Celsius, add 273, and that's the temperature point on the Kelvin scale for the same landmark, freezing point of water. So similarly, go over here to the absolute lowest temperature. It's negative 273 Celsius. Add 273 to that, you get 0 absolute. So to go from Celsius to Kelvin, you add. To go from Kelvin to Celsius, you subtract. But we're going to have like maybe one question on that. Now, I want to talk about, well, I'd love to talk about the SR-71 Blackbird, but what I really want to do is talk about how things heat up. The reason I use this image, these are planes, kind of cool, spy planes developed in the 1960s to keep an eye on the Russians, and all the cool equipment is developed to keep an eye on the Ruskies. Anyways, this one could fly so fast that it's the leading edge of the wings and the control surfaces would glow red hot. It would be so hot it would actually glow. If you could see it during at night, and I actually have seen the SR-71 at night with red hot leading edges. It's kind of cool. I saw that one time out in Montana. Now, let's keep going. I want to talk about heat energy itself. The customary unit for talking about heat energy is the calorie. Now, we also use it for food, and I'll get to that in a few minutes. But a calorie is a unit of energy or work that's defined thermally. It's the amount of energy that it takes to heat up a gram of water that's in a liquid state from 14.5 degrees Celsius up to 15.5 degrees Celsius. Now, the British thermal unit, BTU, you sometimes see that on appliances. It's rated in so many BTUs or whatnot per hour or something like that. The BTU, that's defined in terms of a pound of water, I believe. But we're going to work in calories and of course, joules. And this is considered a metric system. It's using grams and the Celsius scale. Now, the reason that we actually know this to be the case is because of the experiments of James Prescott Joule over 150 years ago, I guess now. And what he did was he rigged up a device kind of like this. This is kind of a idealized drawing of his device. And what he did was take a container of water in here and put a vertical paddle wheel so that as this weight over here, this brass weight dropped, it would cause this paddle wheel to spin. So here's a pulley, and then here's another pulley, kind of mounted vertically like this. And this second pulley here over the canister of water causes, though, if the string is pulled, the paddle wheels down here spin. So if you let the weight drop, a little bit of delta Y, all right, mg delta Y is the gravitational potential energy. Okay, that is stored up here at the top, and it's surrendered back by the time you drop a distance delta Y, and it turns these paddles, all right? And the paddles start to move. Eventually, the paddles stop, but the water keeps moving, and so you say that all the kinetic energy has gone from the falling weight into the water itself. All right, so far so good. Now, what Joule said was, all right, if I do this, I should be able to measure a change in the temperature. So he has a thermometer here mounted with the business end down in the water. So he used different weights, different delta Ys, different amounts of mg delta Y, different amounts of work, different amounts of water, and he measured how much the temperature rose. All right? With his thermometer. And he was able to figure out, okay, for 1 gram, it takes 1 Celsius degree, it takes 1 calorie of work. Right? Now, here's a few more blurbs about it. And of course, we've mentioned this already. 1 calorie raises 1 gram of liquid water by 1 Kelvin, or 1 Celsius degree. And that could be a calorie from sunlight, or a calorie from fire, a calorie from, from friction, rubbing your hands together, or any other source of heat that you can think of. And one way to write that is this way, that for liquid water, it takes 1.00 calorie per gram per Kelvin to raise the temperature. So this is going gram for gram and Kelvin for Kelvin, right? If you want to raise it up a few more kelvins, that's all right. You just got to go at this particular rate. You've got to have so many calories. And if you do, you'll be able to raise the temperature to where you want it. Now, second note, solid water only requires 0.5 calories per gram per Kelvin. Right? So if you have a 1 gram ice cube and at like minus 10 Celsius, so really cold, and you want to raise it up to minus 9 Celsius, it takes half a calorie to do it. Right? And every substance is different. But we would write it down this way, 0.50 calories per gram Kelvin. Now, here's the heart of our discussion for today. What is the difference between liquid phase and solid phase? Well, liquid phase and solid phase for water, the difference is 273 Kelvin. Either you're above it for liquid or you're below it for solid, for ice. Another way to look at it is on a submicroscopic molecular level that crystalline bonds form between the H2O molecules below 273. And those bonds require energy. Okay, it takes energy to break them apart. Okay, it's like a rubber band. It takes stretch to break a rubber band. Okay, and it takes energy to, and this is electrical potential energy. The energy between the hydrogen and the oxygen of two separate water molecules, i.e., hydrogen bonding. That's the intermolecular force that makes beautiful snowflakes. You know, the six-sided design of snow, of ice crystals. All right? And for ice, for any solid, it's an enormous amount of energy that is stored. So if you want to melt something, it takes, let me do this closer to the mic. It takes a lot of oomph, a lot of work to break apart those bonds. For water, one of the interesting properties of water is water stores an enormous amount of thermal energy. It's very hard to heat up. It takes a lot of joules to do it, a lot of calories to do it. Now, this is just looking at water. And if you look at other substances, you're not going to have to memorize any of these thermal properties. I'm going to give you this on the cover sheet for the exam. That's something else I should mention to you. So all these tables that you see in the book, you'll see something like that in the exam. Here's the thermal equivalence of work. So the mg delta y, that's joules of work. For 1 kilogram, 1 meter, 9.8 joules of work. Excuse me. And that's, so 4.184 joules of work from mg delta y raises 1 calorie, raises 1, woo, sneezing here, sorry. 4.184 joules raises 1 gram by 1 Kelvin, i.e. that's equivalent to 1 calorie. Now, second line here on this slide is a food calorie, usually symbolized with a capital C in a science book, but not capitalized on the nutrition facts in a box of Cheerios or a bag of Cheetos or anything like that. But a food calorie is considered to be 1,000 of these thermal calories. Oh, by the way, the other nickname for this calorie here that's equal to 4.184 joules, the gram calorie. Sometimes you'll see it mentioned as gram calorie. Thermal calorie or gram calorie. Now, I have a table here. Don't worry about memorizing it, but do look at it. It's on page 96. It's just a copy from page 96 of your e-text. And on here I've got melting points, boiling points, and density as a solid and as a liquid. And there's a couple interesting things in here. By the way, there's a typo. Let me just point out to you right up here, the density of H2O as a solid should be 0.92. I was thinking of the specific heat, 0.50, when I typed this, I guess. Anyways, go ahead and correct that. Make a note of that for your notes. So let's look at this. 0 and 100 for melting point, boiling point on the Celsius scale. Yeah, we already know about that. Check out ethanol here. The melting point, negative 114 Celsius. That's really cold. So ethanol has to get really, really cold before it'll freeze. Now, you may see somebody that puts a bottle of vodka into their freezer at home to keep it cold. And most people don't have a freezer that will go down to 114 Celsius. All right, so the vodka, it'll freeze water, the refrigerator, the freezer, but it won't freeze that alcohol in the vodka or whatever else you put in there. But now look at this, the boiling point. All right, now this is the point where you break apart the liquid. See, make a note to yourself. The liquid state has weak intermolecular bonds. The liquid state has weak intermolecular bonds. The solid state, or the crystalline state, has strong, tough intermolecular bonds. And the liquid has very weak. And when I say weak, think of a droplet of water. Liquid water it's not able to form a crystal, but it still holds together. It'll form as a sphere. The raindrops, they're actually spherical in shape. So that's the simplest shape that you can find for anything is a sphere, or a three-dimensional shape. And so liquids can hold things into shape, but crystals, have very precise, cool-looking shapes, geometric shapes. Anyways, it's really easy to bust apart the bonds for ethanol. And why is that? It has a pretty low boiling point. 79 is still pretty hot, but it's not, it's not 212 Fahrenheit. It's below that. Because 100 Celsius, that's 212 Fahrenheit. So 79, this stuff will evaporate. It won't evaporate in quickly, but a lot more easily than water. Okay, ammonia, similar. Look at that, minus 33. Now, there's a side note down here about ammonia. Ammonia is a gas at room temperature. We purchase it as an aqueous solution at the store. But if you open up the bottle of ammonia liquid at the store, it'll start to evaporate, and it'll fill the room with ammonia fumes. So you can always smell when somebody's using ammonia, to clean stuff, to mop with and whatnot. And then here are these other metals: aluminum, iron, copper, silver, gold, and lead. Now look at the low melting point for lead. All right, that's pretty low. I mean, it's hot. I mean, it'd burn your hand and everything. But if you were out in the wilderness, with Daniel Boone or something, and you had to make more lead shot to hunt those bears and everything out in Kentucky, you could get this in a campfire. But look at this for iron. Forget about it. That's tough. You know where you can get? Raise your hand if you've ever seen a blacksmith at work, an actual blacksmith. And you know that they have those bellows and they pump the air into their fire to get their fire ultra hot. And why is that? Well, so you can maybe get a little bit of soft. You're not melting that iron, but you're softening it up a little bit. Starting to melt. And look at that temperature, 1538. That is HOT. There's many stars in the universe, the surface of which are not too much higher than 1538 Celsius. So it's, now look at this, boiling point. Whoa, 2861 Celsius. And look at this, gold, 2850. So gold is pretty hard to vaporize. This is the boiling point. So you melt the gold at 1064 Celsius. Okay, that's pretty hot. But then if you want to vaporize it, which why we like to vaporize gold? So that it can be deposited in really thin layers on your electronics. We do a lot of gold-covered, gold-plated electronics because gold is a very excellent conductor. But it's also very expensive, of course. So Yeah, so if you want to vaporize it and then cool it down onto the surface, deposit a very thin level of gold, a very thin layer of gold, yeah, you can do it. But first you got to get into gaseous state at 2856 Celsius. And then add 273 that, and that'll be the Kelvin temperature. All right, now look at this. Here's the density. Check out these densities. This is not, this is just extra data here. But check this out. This is important. Thermally, this is pretty important. H2O, solid, cold, crystalline, ice, 0.92 grams per cubic centimeter. Liquid, 1.00 gram. I mean, that's how we define the gram. 1 cubic centimeter of liquid water, 1.00 grams. Now, look at these metals. Go down here to aluminum. Aluminum, solid is denser than the liquid. Okay, so here's metallic aluminum. Here's liquid aluminum. Okay. Iron, solid iron and liquid iron. Copper, solid copper and liquid copper. Silver, solid silver, molten silver. Gold, solid gold, molten gold. Lead, solid lead, liquid lead, molten lead. Notice anything about this? Pretty close, but so what do you notice about water? Water, correct. Water's the only one that's less dense as a solid. Look at that. Everything else. And that, my wonderful students, is why ice in the North Pole rises, or in a frozen lake, rises to the surface of the water. It doesn't sink to the bottom. Unless it's completely frozen all the way down. But it'll rise to the top. Water has thermal properties that are very, very unusual. Now, let's go to this. Let's go to this diagram, and I'm going to give you some concepts, again, about this idea of intermolecular bonds, breaking them and forming them. You form them by putting in work, and you break them by breaking them apart. Okay, now on this diagram, the energy again is on the horizontal scale. So, and the temperature is in kelvins on the vertical scale over here on the left. Okay, and this is another, as I said, this is an image from your textbook, an illustration from your textbook. So Q, students, Q is the symbol usually used for thermal energy. If you're working on heat or something like that, instead of using E or KE or something like that, if you're working with heat energy, you usually use the symbol Q. But you can use any symbol you want. But we're going to use Q here. And in this diagram, here are the concepts I want to go over with you. To melt or to freeze, so melting and freezing are, one way and then the other way. Same phase transition. Boiling and condensing, same phase transition, different directions. Those are each what you would call dynamical reorganizations of matter. From the heavy crystalline bonds to loose liquid state intermolecular bonds, the cohesion bonds, to gaseous state, no bonds at all, completely unbonded. So every molecule, it's every molecule for itself. Whereas in a liquid state, they're slightly cooperating, and then in a crystalline state, they're totally locked in. Okay, and what that means is that it requires more kinetic energy or less kinetic energy that will prevent or form intermolecular bonds. So if you have molecules that are zipping around really fast, it's like Nerf balls that are coated, that are surrounded by Velcro. So if you have Velcro covered Nerf balls, if they're going really slow, they'll hook up together and they'll bond together. But if they're going really fast, they'll bounce off. The Velcro won't have time to hook up, and they'll bounce off of each other. So you think of it that way. Okay, now look over here on this diagram. Up here is the title: 40 grams of water that goes from 253K to 293K. Now 253K is 20 kelvins below freezing, right? Because freezing is 273. So we're starting 20 kelvins below that at 253. And we're ending at 393. Now that's 20K above boiling, right? So, we're just going 20 degrees. And then there's 100 Kelvin between freezing and boiling, right? And we're doing this with 40 grams, right? Now, I want to focus on this horizontal line segment here. This represents if you're going from left to right, this represents the melting process. On this horizontal line, you're adding energy from Q1 to Q2, all right? So with a flame or with friction or sunlight or something like that. But you're staying at 273. Now make a note of that. When you melt something, it stays at 273. Well, if you melt water, it stays at 273 until it all melts. And then when it's all melted, then you can start heating up the liquid water. Okay, that corresponds to this upward line segment here from Q2 up to Q3. All right, but right here, this horizontal segment, Q1 to Q2, that represents, if you're going left to right, that represents melting, and you're adding energy in the form of sunlight or electrical energy or a burner on your stove, something like that. And that's because you're going from Q1, which is less than Q2. All right? So you're going to a higher energy state. You're adding energy. If you want to melt it, you have to add energy. And that's like I said, it takes energy to bust up all those crystalline bonds. All right? And then when you've got the crystalline bonds done, you've got a liquid. But you got to do them all. Now the other direction, same phase transition, but if you go right to left, that would be freezing. You've got some warm liquid, and you've gotten it down to 273. But now you've got to freeze all of it at 273. And it takes 80 calories per gram to do that. So this is a case when you're going to the left from higher energy Q2 to a lower energy Q2, you have to remove 80 calories per gram. Okay, so 80 times 40 is 3,200 calories. So this line segment symbolizes 3,200 calories removed by whatever refrigeration process you care to name. Okay, so we're going to lower Q's for this freezing procedure here. Now, back to this one. As I've mentioned, for boiling points and melting points, everything is different. Every substance has to be measured. Same thing with this. To the amount of energy to melt a gram of anything, the amount of energy to vaporize a gram of anything, it's tough to predict, but you just measure them in the lab. So for this table here, this is from page 91, and we're going to focus on the last two columns, latent heat of fusion and latent heat of vaporization. Right now, the fourth column, latent heat of fusion, what that means, you can add this to your notes. The latent heat of fusion is the amount of energy that you have to bust up all those intermolecular bonds between water molecules in the ice state. So it takes 80 calories. So for every gram of ice that you have at 273, all right, you're at the melting point, but you need more energy to bust up the bonds. You've heated it up to 273 Kelvin. Now you need 80 more calories for every gram. So this is gram by gram for gram. Water takes 1 calorie, or excuse me, water takes 80 calories to melt. Now, gram for gram, look at ethanol. Ooh, ethanol's, if you can solidify it, if you can freeze it, and then you want to remelt it again, it only takes 24.9 calories per gram for ethanol. And here's copper. Whoa, look at gold. To melt gold, that's a walk in the park. 50, way less than melting ice. Matter of fact, ice is the hardest thing on this list to melt. Look at lead, 5.5. That's the easiest of all. Once you get it up to the melting point, all right? And lead's pretty easy to get up to the melting point, actually. Now over here, this is the other phase transition from liquid to gas, or condensing gas to liquid, all right? And whoa, check this out. From liquid water to water vapor, dude. And now you can see why a hurricane has such a drastic effect. There's an enormous amount of heat energy in the water vapor. And when that all condenses back into rain, you got a lot of energy on your hands. Right? So that complex storm that we were dealing with, Hurricane Matthew, it's all about this stuff right in here. All these thermal properties for water. It's incredible. Now, you can look at this on page 91. Here's kind of a summary outline. Just kind of some vocabulary here. Phase transitions. From liquid to solid, we would either call it freezing. Usually that's for something like water or ammonia or ethanol or something. Or we would say solidify if it was a metal. We don't usually say, well, I'm gonna freeze some melted gold. What you usually say is just let it solidify as it cools. Liquid to gaseous, that's boil or vaporize. Those are the two words we use for that. Solid to gaseous, that's the one that CO2 does here on the surface of Earth. Sublimation. Solid to liquid, that's melting. CO2 does not do that under normal atmospheric pressure. Gaseous to liquid, that's rain, condensation. That's dew forming on the windshield of your car on an early morning. Gaseous to solid, that's when you have gold heated up into a vapor and then you cool it rapidly and it deposits a thin layer of solid gold onto some surface that you're trying to work with. So in general, the gaseous state is the higher energy state, and the lower energy state is the solid, and liquid is kind of in between. And every, excuse me, boy, every substance is different, so you just got to measure it. And let me repeat, on the exam, you will not have to memorize those tables. I'll give you the tables that you need to make decisions and to think you'll have on the cover page, or maybe in the question itself. And last comment about phase transition, the pressure, the ambient pressure also has an effect. In other words, for CO2, if you're at high pressure, you can get CO2 to melt down to a liquid. Now here's CO2 ice, or dry ice. We're going to tackle this next week, so you don't have to worry about it for the exam. But under certain conditions, yes. We're not dismissed yet. I still have to talk about exam 2. If you don't want to do good on exam 2, you can leave if you want. But if you, yeah, good. All right. Anyways, we're going to tackle CO2 dry ice next week. Now, tonight homework, our regular homework, it'll be I'll try to make it short, and a short study assignment. Try to get that available for you by supper time. And I know it's crushing up against Thursday, but you know it's always like this. The Tuesday lecture before a midterm, it's always kind of a. Now, last few comments about exam 2. Make sure that you can handle stopping time, stopping distance problems. And there's several variations of those problems. All right? If you want to crush the test, you want to, among other things, you want to be able to crush those kind of problems. You will have some calculations. Now, we've been having a little bit of difficulty with the clickers, but I think we're going to be okay to use clickers for calculations. So there's going to be some serious calculations in the clicker portion. Now, I might put a basic calculation in there as well. You will have matching formulas as before. You will have tables of thermal melting points and latent heat of fusion and all that stuff. If you need it, it will be on the cover page or possibly embedded in the question itself. So I might say, as you know, the latent heat of fusion of water is 80 calories per gram. So for that, tell me what and then I'll ask you a question and you have to answer it. So I might do that, or it might be on the cover page. Bring your eye clicker. I'm not looking at anybody. I know that last time there was a couple people that got caught napping. They were slacking for whatever reason. So anyways, make sure you have good batteries. Bring your eye clicker. And definitely bring a regular calculator. You're definitely going to need it. Any questions from the floor? Okay, you're dismissed. I'll see you on Thursday. Be here as early as you can.